for me.
So today we're getting started on our unit on linear functions, and we're starting with linear equations. Now an equation is when you write this thing is equal to that thing. And really all that does is makes a relationship. These two things are the same. Now that's not the only relationship that exists in algebra, but it's the one we use most often because when these two things are the same, we can do some very specific things to those two things and never actually change them. So an equation is the mathematical statement that these two things are equivalent. We call it a linear equation in one variable when there's only one variable in there. Linear because if we were to draw it on a graph, it would make a single line. Later we do things which are much more complicated and draw curvy lines and all sorts of other strange lines, but that's later. So I explained in Algebra Solves Mysteries that we can solve this to find out what's in X. I wasn't completely accurate when I said that. It wasn't that I was lying to you, it was just that we look at it a slightly different way when we get on a higher plane. It's not that there's something hidden inside X. It's that there's only one value of X that makes this relationship true. And our job is to find out what that value is. In this simple example, we divide both sides by 5 and find that X is 6. Again, it's not that 6 is what's in X. It's that 6 is the only X that keeps this relationship true. We call those numbers the solution set, all those values that make the relationship come up true. In this case, the solution set has one number, 6. Now, the beautiful part of having a relationship like this is that as long as I do the same thing to both sides, the relationship stays true. Let me show you. I have 5x equals 30, just like we saw before. What if I were to add 4 to this side of the scale? Well, the scale's going to go down on that side. It's heavier. But if I add 4 to the other side, the relationship stays true and has the same solution set that it had before. Now, what I said in Algebra Solves Mysteries is that as long as we use the equality properties, the relationship stays true. There are 4 equality properties. The first is called the addition property of equality. And it says if I have a relationship, maybe it's got a minus in it that I don't like, I can add 7 to this side as long as I add 7 to this side. I'll get x equals 19. The second rule is called the subtraction property of equality. It says if I have some relationship and I have some plus in there that I don't like, I can subtract from both sides and get the same relationship, only simplified. Caution. If this were a set of scales with the balance right here in the center, if I added something to one side or subtracted, I'd want to add or subtract to the other side just once. If I do it twice, I'm not actually doing the same thing to both sides. For that reason, an example like this, I'm subtracting 2 from here, but that doesn't mean I want to subtract 2 from here as well. That would be subtracting twice from the same side. I want to subtract from this side once from each side to keep the relationship true. There are 2 more properties. The next one is the multiplication property of equality, which simply states that if I have a legal relationship, I can multiply something to both sides and it'll stay true. In this case, I can get rid of the 1/3 by multiplying times 3. Perfectly legal as long as I do it to the other side as well. 3 times 1/3 x leaves me with just x. And 5 times 3 is 15. The last one is the division property of equality. If I have something multiplied and I don't want it to be, I can divide by both sides. Divide this side by 8, divide the whole thing, and you get just x. But I have to divide this side by 8 to keep the relationship even. 24 divided by 8 is 3. Caution, if I had a scale with the balance here in the center, if I cut one side in half, I have to cut the other side in half, but I want to cut it in half all together, the whole thing cut in half, which means I can't just cut this by 8, because that's only cutting this part. I'd have to also cut this part by 8, while I'm also cutting the other side by 8. For this reason, we usually wait to do our multiplying and dividing until the last step, so we really only have one thing on each side to multiply or divide. And we can combine those things. Let's take a look. Here I have a relationship. It has a solution. I just don't know what it is yet. We're going to use the properties of algebra to find out. Let's see. There's my balance point. My problem is I have a 6 times all of this. There's actually two ways I could go. I could take 6 times x and 6 times negative 3, distribute, but I'm going to hold off on that. Right now I just want to kill that divide by 6. So I'm going to divide this whole side by 6. Perfectly legal as long as I also do it to this side. 6 over 6 cancels. That'll leave me with just x minus 3 on the right side. My balance is still here, and negative 30 divided by 6 is negative 5. Remember, a negative divided by a positive is a negative. Got another perfectly good relationship, same as it was before, only now it has a negative 3, a minus 3 on it. What I created was another perfectly good relationship with the same solution set. Now, let's get it so it just says x. It has a minus 3 on it, so we're going to use the addition property of equality and add 3 to both sides and find that x, that cancels, is negative 2. What? Why is it written backwards? In algebra, we don't care if you say negative 2 is x or x is negative 2. It means the same thing. So if it makes you more comfortable, write it the right way. One more big example. Here's a relationship. It has a balance point in the center. These two things are equal to each other, and I can solve the mystery of what x would make this relationship true using those equalities of algebra. Let's see. I have numbers on both sides. I'd rather have the numbers on one side. So I'll take this negative one and get rid of it. I'll add 7 to both sides. Perfectly legal here as long as I also do it over here. That gives me 6x equals 2x plus 24. Now what I have is x's on both sides. To really find out what's in the x, I needed to say x equals number. So let's get this smaller x that's over here with the number away from the number. Let's get rid of it. Perfectly legal to take away 2x, 2 buckets of whatever's in the variable, as long as I take it away from the other side. 2x minus 2x cancels those out entirely. 6x minus 2x means I have 4x left. And on this side, 24. Another perfectly good relationship. It has the same solution set as the one we started with, and I'm one step away from solving the mystery of what x can contain to keep it true. We'll divide both sides by 4 and find that x is 24 divided by 4, 6. 6 is the only number that left this original relationship true. Proof? No problem. If x was 6, I'll plug that in. 6 times 6 makes 36, minus 7. 2 times 6 makes 12, plus the original 17. 36 minus 7 is 29. 12 plus 17 is 29. True. Try it with something else. What if x had been 5? 6 times 5 would make 30 minus 7. And 2 times 5 would make 10 plus 17. 30 minus 7 is 23. 10 plus 17 is 27. Not true. So 6 is in the solution set. 5 and any other number is not. There you go. The very basics of algebra, the rules of equality. Next time, we're going to show you that sometimes those relationships aren't exactly what they seem.
Oh, I'm a happy boy. Oh, I'm a happy boy.